Hello and welcome to another Crafting Interpreters video. In this series of videos, we are going to be reading the book Crafting Interpreters by Robert Nystrom. You can read the whole book for free at craftinginterpreters.com. And in this video, I think, if I remember correctly, we are going to be implementing basic arithmetics with correct order of operations using our programming language written in Go, and this corresponds roughly to the to chapter 5 of his book. And in the previous video, which has the number 3, we implemented the scanner, and this scanner presently works kind of like this. If you run it with a simple arithmetic equation, it's going to be to parse it into several tokens, including an end of file token. And I think in this video we're going to be working on converting that syntax to an actual abstract syntax tree. Also, you may notice that I now have a different setup because I finally decided to come out as a macOS user. And yep, without further ado, I'm going to continue reading the book. And I think I'm pretty much sure we ended up reading about the ham and hollandaise and the eggs benedict, because after I finished recording the previous videos, I went to Carrefour and bought bread. Yep. Anytime we hit a rule that had multiple productions, we just picked one arbitrarily. If it is this flexibility that allows a short number of grammar rules to encode a combinatorially larger set of strings. The fact that a rule can refer to itself, directly or indirectly, kicks it up even more, letting us pack an infinite number of strings into a finite grammar. Enhancing our notation. Stuffing an infinite set of strings in a handful of rules is pretty fantastic, but let's take it further. Our notation works, but it's tedious. So, like any good language designer, we'll sprinkle a little syntactic sugar on top. Some extra convenience notation. In addition to terminals and non-terminals, we'll allow a few other kinds of expressions in the body of a rule. Instead of repeating the rule name each time we want to add another production for it, we'll allow a series of productions separated by a pipe, as in bread can be toast or biscuits or an English muffin. And further, we'll allow parentheses for grouping and then allow pipe within that to select one from a series of options within the middle of a production. Such as protein could be scrambled or poached or fried eggs. Using recursion to support repeated sequences of symbols has a certain appealing purity, but it's kind of a chore. It's kind of a chore to make a separate named subrule each time we want to loop. So we also use a postfix asterisk to allow the previous symbol or group to be repeated 0 or more times, such as crispiness could be really, or really and then really with an asterisk. A postfix plus is similar but requires the preceding production to appear at least once. A postfix is for an optional production. The thing before it can appear 0 or 1 time, but not more. Protein with potential breakfast on the side. Side note, this is how the scheme programming language works. It has no built-in looping functionality at all. Instead, all repetition is expressed in terms of recursion. With all of these syntactic niceties, our breakfast grammar condenses down to breakfast can be a protein with optional breakfast on the side, or bread. And then protein could be really, and really could be repeated one or more times. Crispy bacon, or a sausage, or eggs that could be scrambled, poached, or fried. Then we have bread, which could be toast, biscuits, or an English muffin. Not too bad, I hope. If you're used to grep or using regular expressions in your text editor, most of the punctuation should be familiar. The main difference is that symbols here represent entire tokens, not single characters. We'll use this notation throughout the rest of the book to precisely describe Lox's grammar. As you work on programming languages, you'll find that context-free grammars using this or EBNF, which is extended Bacchus-Naur form, help you crystallize your informal syntax design ideas. They are also a handy medium for communicating with other language hackers about syntax. The rules and productions we define for Lox are also our guide to the tree data structure we're going to implement to represent code in memory. Before we can do that, we need an actual grammar for Lox, or at least enough of one for us to get started. 513, a grammar for Lox expressions. In the previous chapter, we did Lox's entire lexical grammar in one fell swoop. Every keyword and bit of punctuation is there. The syntactic grammar is larger, and it would be a real bore to grind through the entire thing before we actually get our interpreter up and running. Instead, we'll crank through a subset of the language in the next couple of chapters. Once we have that mini language represented, parsed, and interpreted, then later chapters will progressively add new features to it, including the new syntax. For now, we are going to worry about only a handful of expressions. Literals, numbers, strings, booleans, and nil. Unary expressions, a prefix bang to perform a logical not, and minus to negate a number. Binary expressions, the infix arithmetic plus, minus, asterisk, and slash, and logic operators equals equals, bang equal, less than or equal, greater than unequal, we know and love. Parentheses, a pair of left paren and right paren wrapped around an expression. That gives us enough syntax for expressions like 1 minus left bracket 2 asterisk 3 right bracket, not bracket, left parentheses, left paren 2 times 3 right paren is less than 4 equals false. Using our handy dandy new notation, here is a grammar for those. An expression could be a literal, a unary expression, a binary expression, or a grouping expression. And a literal would be a number, string, true, false, or nil. Then a grouping expression will be an expression in parentheses. A unary expression would be an expression preceded by a minus or a bang. And a binary operator expression would be an operator with two expressions on the sides. And then an operator could be any one of the operators we have described above. There is one bit of extra meta syntax here. In addition to quoted strings for terminals that match exact lexemes, we capitalize terminals that are a single lexeme, whose text representation may vary. Number is any number literal, and string is any string literal. Later we'll do the same for identifier. Side note, if you're so inclined, try using this grammar to generate a few expressions like we did with the breakfast grammar before. Do the resulting expressions look right to you? Can you make it generate anything wrong, like 1 plus /3? I don't think we can, because this plus wouldn't match this plus needs an expression or both sides, and while 1 could be an expression in and of itself, /3 does not work like this, so sorry. This grammar is actually ambiguous, which we'll see when we get to parsing it, but it's good enough for now. 5.2 Implementing syntax trees. Finally, we get to write some code. That little expression grammar is our skeleton. Since the grammar is recursive, note how grouping, unary, and binary all refer back to expression. Our data structure will form a tree. Since this structure represents the syntax of our language, it's called a syntax tree. Side note, in particular, we are defining an abstract syntax tree. In a parse tree, every single grammar production becomes a node in the tree. An AST elides productions that are needed by later phases. Our scanner used a single token class to represent all kinds of lexemes. To distinguish the different kinds, think the number 1 to 3 versus the string 1 to 3, we included a simple token type enum. Syntax trees are not so homogeneous. Unary expressions have a single operand, binary expressions have 2, and literals have none. Side note, tokens aren't entirely homogeneous either. Tokens for literals store the value, but other kinds of lexemes don't need that state. I have seen scanners that use different classes for literals and other kinds of lexemes, but I figured I'd keep things simpler. We could mash that all together into a single expression class with an arbitrary list of children. Some compilers do. But I like getting the most of Java's type system, so we'll define a base class for expressions. Then for each kind of expression, each production under expression, we create a subclass that has fields for the non-terminals specific to that rule. This way we get a compile error if we say, try to access the second operand of a unary expression. We could, sorry, I had to make a break. We could mash that all together into a single expression class with an arbitrary list of children. Some compilers do, but I like getting the most out of Java's type system, so we'll define a base class for expressions. Then for each kind of expression, each production under expression, we create a subclass that has fields for the non-terminals specific to that rule. This way we get a compile error if we say try to access the second operand of a unary expression, something like this. Also, this is obviously not possible with Go because Go doesn't have inheritance. We could try to embed class if we feel so inclined, but I'm not entirely sure if this is a good idea. Maybe we'll just see what the author tries to implement and then try to somehow implement it in Go. Side note, I avoid abbreviations in my code because they trip up a reader who doesn't know what they stand for. But in compilers I've looked at, expr and steamed STMT are so ubiquitous that I may as well start getting used to them now. Expr is the base class that all expression classes inherit from. As you can see from binary, the subclasses are nested inside of it. There's no technical need for this, but it lets us cram all of the classes into a single Java file. 5.2.1 Disoriented objects. You'll note that, much like the token class, there aren't any methods here. It's a dumb structure. Nicely typed, but merely a bag of data. This feels strange in an object-oriented language like Java. Shouldn't the class do stuff? The problem is that these three classes aren't owned by a single domain. Should they have methods for parsing, since that's where the trees are created? Or interpreting, since that's where they are consumed? Trees span the border between those territories, which means they are really owned by neither. In fact, these types exist to enable the parser and interpreter to communicate. That lends itself to types that are simply data with no associated behavior. This style is very natural in functional languages like Lisp and ML, where all data is separate from behavior, but it feels odd in Java. Functional programming aficionados right now are jumping up to exclaim, "See, object-oriented languages are a bad fit for an interpreter." I won't go that far. You'll recall that the scanner itself was admirably suited to object orientation. It had all of the mutable state to keep track of where it was in the source code, a well-defined set of public methods, and a handful of private helpers. My feeling is that each phase or part of the interpreter works fine in an object-oriented style. It is the data structures that flow between them that are stripped of behavior. 5.2. Metaprogramming the trees. Java can express behaviorless classes, but I wouldn't say that it's particularly great at it. 11 lines of code to stuff free fields in an object is pretty tedious, and when we're all done, we're going to have 21 of these classes. I don't want to waste your time or my ink writing all that down. Really, what is the essence of each subclass? A name and a list of typed fields. That's it. We are smart language hackers, right? Let's automate. Side note, picture me doing an awkward robot dance when you read that. Automate. Instead of tediously handwriting each class definition, field declaration, and constructor and initializer, we'll hack together a script that does it for us. It has a description of each tree type, its name and fields, and it prints out the Java code needed to define a class with that name and state. Okay, this script is a tiny Java command line app that generates a file named expert.java. Side note, I got the idea of scripting the syntax tree classes from Jim Huguenin, creator of Jython and IronPython. I'm going to look up his name so that we know how to pronounce it. Okay, there is nothing about him. The script is a tiny Java command line app that generates a file named expert.java. Okay. Yeah, actually, I think we could. We could technically just try and write it all by hand, because Go is not Java. Go doesn't require all of this magic. So, on the other hand, I don't think there is going to be an easy way to... Oh yes, we could just define expert as an interface, right? Okay, I think we're going to have to figure it out. I'm going to move this to the left side of the screen, and this means the layout is broken, and I'm going to try and write some code in expr.go. So I'm going to define an expert type, which is going to be an interface, an empty interface, like so. Then we're going to define a binary type, type binary, which is going to be a struct. It's going to have a left expression. It's going to have a token, which is an operator. and no, it's going to have an expression on the left, an operator which is a token, and then it's going to have a right which is an expression. Okay, type grouping struct, it basically just wraps an expression. Okay, and then type literal struct, it's going to contain a value which is going to be any, and then a unary, type unary struct, it contains a token, an operator which is a token, and an expression right which is an expression. Also, probably we could replace those expressions in here with pointers to save some space, I guess. I mean, to avoid copying. Okay. For brevity's sake, I jumped the descriptions of the expression types into strings. Each is the name of the class followed by a colon and a list of fields separated by commas. Okay, I'm just going to skip this because we don't really need to implement it. And okay, there we go. There we go. All of that glorious Java boilerplate is done. It declares each field in the class body. It defines a constructor for the class with parameters for each field and initializes them in the body. Compile and run this Java program now, and it blasts out a new .java file containing a few dozen lines of code. That file is about to get even longer. Appendix 2 contains the code generated by this script code once we've finished implementing JLogs and defined all of its syntax tree nodes. Let me see. Okay. Yeah, I'm going to skip it for now. But I mean, at least we have interfaces, right? So a lot of things that can be done with interfaces in Java can be done with interfaces in Go, I guess. Put on your imagination. Okay, section 5.3, working with trees. Put on your imagination hat for a moment. Even though we aren't there yet, consider what the interpreter will do with the syntax trees. Each kind of an expression in logs behaves differently at runtime. That means the interpreter needs to select a different chunk of code to handle each expression type. With tokens, we can simply switch on the token type. But we don't have a type enum for the syntax trees, just a separate Java class for each one. We could write a long chain of type tests, like so, but all of those sequential type tests are slow. Expression types whose numbers are alphabetically later would take longer to execute because they'd fall through more if cases before finding the right type. That's not my idea of an elegant solution. We have a family of classes and we need to associate a chunk of behavior with each one. The natural solution in an object-oriented language like Java is to put those behaviors into methods on the classes themselves. We could add an abstract interpret method on the expr, which each subclass would then implement to interpret itself. This exact thing is literally called the interpreter pattern in design patterns, elements of reusable object-oriented software by Eric Gamma et al. This works alright for tiny projects, but it scales poorly. Like I noted before, these three classes span a few domains. At the very least, both the parser and interpreter will mess with them. As you'll see later, we need to do name resolution on them. If our language was statically typed, we'd have a type checking pass. If we added instance methods to the expression classes for every one of those operations, that would smash a bunch of different domains together. That violates separation of concerns and leads to hard to maintain code. 531. The expression problem. This problem is more fundamental than it may seem at first. We have a handful of types and a handful of high-level operations like interpret. For each pair of type and operation, we need a specific implementation. Picture a table. Rows are types and columns are operations. Each cell represents the unique piece of code to implement that operation on that type. An object-oriented language like Java assumes that all of the code in one row naturally hangs together. It figures all the things you do with a type are likely related to each other, and the language makes it easy to define them together as methods inside the same class. This makes it easy to extend the table by adding new rows. Simply define a new class. No existing code has to be touched. But imagine if you want to add a new operation, a new column. In Java, that means cracking open each of those existing classes and adding a method to it. Functional paradigm languages in the ML family flip that around. There you don't have classes with methods. Types and functions are totally distinct. To implement an operation for a number of different types, you define a single function. In the body of that function, you use pattern matching, sort of a type-based switch on steroids, to implement the operation for each type all in one place. Side note, ML, short for meta language, was created by Robin Milner and friends and forms one of the main branches of the great programming language family tree. Its children include SML, CAML, OCaml, Haskell, and F#. Even Scala, Rust, and Swift bear a strong resemblance. Much like Lisp, it is one of those languages that is so full of good ideas that language designers today are still rediscovering them over 40 years later. Back to the text. This makes it trivial to add new operations. Simply define another function that pattern matches on all of the types. But conversely, adding a new type is hard. You have to go back and add a new case to all of the pattern matches in all of the existing functions. Each style has a certain grain to it. That's what the paradigm name literally says. An object-oriented language wants you to orient your code along the rows of types. A functional language instead encourages you to lump each column's worth of code together into a function. A bunch of smart language nerds noticed that neither style made it easy to add both rows and columns to the table. They call this difficulty the expression problem because, like we are now, they first ran into it when they were trying to figure out the best way to model expression syntax tree nodes in a compiler. Side note, languages with multi-methods, like Common Lisp's CLOS, Dylan, and Julia, do support adding both new types and operations easily. What they typically sacrifice is either static type checking or separate compilation. People have thrown all sorts of language features, design patterns, and programming tricks to try to knock that problem down, but no perfect language has finished it off yet. In the meantime, the best we can do is try to pick a language whose orientation matches the natural architectural themes in the program we are writing. Object orientation works fine for many parts of our interpreter, but these three classes rub against the grain of Java. Fortunately, there's a design pattern we can bring to bear on it. 532, the visitor pattern. The visitor pattern is the most widely misunderstood pattern in all of design patterns, which is really saying something when you look at the software architecture excesses of the past couple of decades. The trouble starts with terminology. The pattern isn't about visiting, and the accept method in it doesn't conjure up any helpful imagery either. Many think the pattern has to do with traversing trees, which isn't the case at all. We are going to use it on a set of classes that are tree-like, but that's a coincidence. As you will see, the pattern works as well on a single object. The visitor pattern is really about approximating the functional style within an OOP language. It lets us add new columns to that table easily. We can define all of the behavior for a new operation on a set of types in one place without having to touch the types themselves. It does this the same way we solve almost every problem in computer science, by adding a layer of indirection. Before we apply it to our auto-generated expression classes, let's walk through a simple example. Let's say we have two kinds of pastries, beignets and crawlers. A beignet, pronounced beignet with equal emphasis on both syllables, is a deep fried pastry in the same family as donuts. When the French colonized North Africa in the 1700s, they brought beignets with them. Today in the US, they are most strongly associated with the cuisine of New Orleans. My preferred way to consume them is fresh out of the fryer at Café du Monde, piled high in powdered sugar and washed down with a cup of café au lait, while I watch tourists staggering around, trying to shake off their hangover from the previous night's revelry. Okay, so we have an abstract class of pastry and two concrete classes for a beignet and a crawler, and we want them to be able to define new pastry operators, cooking them, eating them, decorating them, etc., without having to add a new method to each class every time. Here's how we do it. First, we define a separate interface. Okay. In design patterns, both of these methods are confusingly named visit, and they rely on overloading to distinguish them. This leads some readers to think that the correct visit method is chosen at runtime based on its parameter type. That isn't the case. Unlike overriding, overloading is statically dispatched at compile time. Using distinct names for each method makes the dispatch more obvious and also shows you how to apply this pattern in languages that don't support overloading. Each operation that can be performed on pastries is a new class that implements that interface. It has a concrete method for each type of pastry that keeps the code for the operation on both types, all nestled snugly together in one class. Given some pastry, how do we route it to the correct method on the visitor based on its type? Polymorphism to the rescue. We add this method to pastry. We add an abstract void accept pastry visitor. Each subclass implements it. Okay. To perform an operation on a pastry, call its accept method and pass in the visitor for the operation we want to execute. The pastry with specific subclasses overriding implementation of accept turns around and calls the appropriate visit method on the visitor and passes itself to it. That's the heart of the trick right here, right there. It lets us use polymorphic dispatch on the pastry classes to select the appropriate method on the visitor class. In the table, each pastry class is a row, but if you look at all the methods for a single visitor, they form a column. We added one accept method to each class, and we can use it for as many visitors as we want without ever having to touch the pastry classes again. It's a clever pattern. Okay, this is going to be like one problem I can see with it is that we're going to have to make sure that all of our expressions here actually implement the EXPR interface, because at least if they are being used in that capacity, because the expression interfaces in Go are not declared, they are implemented by defining methods that match the definition, like as in the interfaces in Go are implemented just by making sure that your type implements all the necessary methods. So if we never use some method on an interface, well, whatever, we will see. Okay, let's weave it into our expression classes. We'll also refine the pattern a little. In the pastry example, the visit and accept methods don't return anything. In practice, visitors often want to define operations that produce values. But what return type should accept have? We can't assume every visitor class wants to produce the same time, so we'll use generics to let each implementation fill in a return type. Oh my. Another common refinement is an additional context parameter that is passed to the visit methods and then sent back through as a parameter to accept. That lets operations take an additional parameter. The visitors will define in the book don't need that, so I omitted it. First, we'll define the visitor interface. Again, we nest it inside the base class, so we can keep everything in one file. Okay. Door. Can we define generic interfaces? No. Can we define generic interfaces at all? Okay, it does not seem like we can. It doesn't really seem like we can define generic interfaces, right? Okay, I guess we could just do something like visit binary expr, and expr is going to be binary, and it's going to, we'll see if there's any way we can somehow return things. Visit grouping expr grouping and we don't really have to define the names for these parameters, and then visit literal expr and this is going to contain a literal, and then visit unary expr unary. And then we know that the expr will have to accept and okay, maybe we could accept wait, go generic interface. Okay, so it looks like we actually can define interfaces like so. Does this mean that does this mean that this is going to contain, okay, so, and this is going to be accept visitor of R, and this is going to return an R, okay. And then we can treat this as an interface rather than a specific type, and then we don't need to pass these as pointers. And that will mean we are going to need what are we going to need? Yeah, we'll see how it actually works out. When we debug our parser and interpreter, it's often useful to look at the parse syntax tree and make sure it has the structure we expect. We could inspect it in the debugger, but that can be a chore. Instead, we like some code that, given a syntax tree, produces an unambiguous string representation of it. Converting a tree to a string is sort of the opposite of a parser, and is often called pretty printing when the goal is to produce a string of text, but is valid syntax in the source language. That's not our goal here. We want the string to very explicitly show the nesting structure of the tree. A printer that returned 1 plus 2 times 3 isn't super helpful if what we were trying to debug is whether operator precedence is handled correctly. We want to know if the plus or asterisk is at the top of the tree. To that end, the string representation we produce isn't going to be log syntax. Instead, it will look a lot like, well, Lisp. Each expression is explicitly parenthesized, and all of its sub-expressions and tokens are contained in that. Given a syntax tree like this, it produces this, okay. Not exactly pretty, but it does show the nesting and grouping explicitly. To implement this, we define a new class. Okay, and this goes to AST printer. And what does it say here? Cannot use generic type expr R of any. Okay. Does this mean that we are going to need... Okay. Oh my, we're going to have to define these generics for everything, right? Thanks, Obama. Does this mean that, okay, does this also mean that the literal is, okay, thanks, Obama. AST printer, let's go. Okay, type AST printer, and we cannot, no, okay. You can define it as an empty struct, right? And then okay, well, AST printer, it has a method called print, and it takes an expression. Of any. Can pass the text so. It returns a string. This is definitely going to be quite a lot of generics for me. I've never used so many generics in Go. And it returns expr accept. This is going to have return expr. Wait, expr. Does it expr not have accept? Method must have no type parameters. Okay. Okay, cannot use expression except p value of interface type any as string value in return statement needs type assertion. Cannot use p variable of type AST printer as visitor any. Okay, it doesn't. This means it does not implement this binary expression yet, and that's why we're going to have to implement it here. Okay, AST printer visit binary expression, and this is going to be expr binary. And string, it returns a string. Return parenthesize. Okay, I guess this is going to be a helper. Okay. Okay, I'm just going to try and port these methods, and later on we'll see how to actually get it to work. If expression value equals nil, return nil, and then return expression value string. Okay, maybe we can just... Can we really assume it's a stringer? No, we cannot. I'm just going to do it for now. It probably is... Yeah. We could probably do something like this. Switch expression value type case float 64 returns through conf for but float This is so complicated. Why does it have to be so complicated? Format float. Okay, I need examples. Go doc strconf format float. Are there any examples? Like seriously. pkg go dev strconf, and do we have format float? Example. I don't want an E, so maybe I could just make it like, yeah, I guess I'll just make it expr value and then G and then -1 and 64 case string return something like this, I guess, plus expr value plus this. We just escape it. This is going to be a string like so. Cannot convert. Okay, we need to express that it's going to be a string like so. And this is going to be a float 64. And in the default case, we're just going to make it return fmt sprintf v like so, and we'll just make it figure it out on its own. Okay, I have no idea if any of this is going to work. And visit unary expression. Okay. past printer visit unary expression expr unary of any return parenthesize expr operator like seam expr right. Okay. Literal expressions are easy. They convert the value to a string with a little check to handle Java's null, standing for lox's nil. The other expressions have sub-expressions, so they use this parenthesize helper method. Okay. Sorry. Blank parenthesize and name string. And this is going to be args. And this is going to be expression. Okay, like so. So, yeah, actually we could do it with a string builder as well. String. I'm pretty sure we have a string builder, right? go doc string builder. Okay, I have to look for it. I'm pretty sure there's also a string builder in the standard library. Or maybe was I mistaken? Okay, it's strings.builder, okay. Yeah, okay. Great. So builder append. Okay, write run. Builder write string and name, and then for expression in args, or I could just call it express like here, in the range, builder write run space, and builder write string. Oh, and this also needs to be a helper, a method. P parenthesize and P parenthesize and P parenthesize. Write string expression accept P. Wait, why? Cannot use expression, need type assertion. Cannot use P as visitor any. Okay, we're going to have, okay, we have to make an assertion like this, and this returns a string, and this P parenthesize, and this also needs to return a string. Okay, builder write run return builder string. What about this? Cannot use P. We want this binary expression any. Okay. Need type assertion. Okay. Cannot use P parenthesize. Okay. Can't use P parenthesize as string value. There's the printer. Okay, well, this is going to be a bit problematic, actually. I think I'm going to need some more. I think I'm going to need some research on it. Is the printer visitor? No, it's not visitor and it's a visitor of string, right? Okay, we want a visitor string, right? Visit one visit binary expression string type parameter. Okay. And this is going to be grouping of string, 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 and then type nil. So no. 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 Cannot use X for left. Visitor string string won't accept visitor any. Okay, maybe if I just remove all of these. Any. Okay. Basically throwing all the type checking out of the window. Can it use generic okay, any. Can it use p variable of visitor any. Wrong type for method visit binary expression. Why so? Okay, we want to return any. And can it use p variable of type AST printer as visitor any. AST printer. Okay, we were returning a string and we want to return an any. Can we do it like so? Visit grouping expression. P as a visitor of type string. Okay, so we can do it like this. Oh my. Can it use p variable of type as visitor any value in argument expression accept? Okay, when we okay, but that also means that maybe we could try to define okay, but that does not mean that an expression has to, or does it? Okay, now the value can be an any, right? And then so we can do it like as R is going to be a string. Visit binary expression, any visit binary expression. Okay, so this way. Accept visitor string expression any. Okay. Visitor expression string. Accept. Okay. I think this is the last error. Okay, this is not an interface. And lo and behold, we got rid of all the. So basically, we just need to claim that everything has the same generic type. And does it even compile? It does. I mean, we haven't used it yet. Okay. It takes a name of a list and a list of okay. Yes, so we did implement the AST printer using the visitor pattern. And I think in the next video we're going to see if we can actually get it working. As in, can we actually get it to print strings from our source code? And until then, I think I'm going to wrap it up for today. The name is Karol Moros, and you have been watching Make Programming Fun Again.